Yes. Can you see my slides?
Yes.
Okay, and you hear me, I can understand. All right, I understand that time is tight, so I will try to speak fast. Here is, first of all, the title of my talk, and also the collaborators with whom I've been doing this work over the past few years. So, sorry, I just have to do this like this. First, I'll give you an overview of the talk. I will briefly mention the enormous progress that has been made in amplitude calculations in gauge theories for the last, let's say, 20 years. And that has had also surprisingly impact in gravity due to this kind of double copy relation, which views gravity and really identifies gravity as a square in a very precise sense of Yang-Mills theory. And then I'll talk about classical general relativity from the loop expansion. So this talk is about how to derive observables in classical general relativity from quantum field theory. And I'll have to be fast, but I'll mention the difference between a post-Newtonian, which you may have heard of, and a post-Minkowskian expansion in general relativity. The kind of expansion I will be talking about is the post-Minkowskian one. It's not as well known as the post-Newtonian one, and I'll explain the difference. So the first step is to start with Yang-Mills amplitudes. It's a well-known subject, but there is a neat way of writing Yang-Mills amplitudes that are independent of color. So we're used to having Yang-Mills amplitudes have their, of course, their color charges, but there is behind that, there is a kind of universal Yang-Mills theory, which is color stripped. So that is if you see the left-hand side of this equation, the first equation, this is the full amplitude, and one can expand that in a kind of basis of the color factors, and the coefficients of that in that basis, they are what is called the color ordered amplitudes. They do not carry indices. They don't have the group indices in them, so they're kind of scalar amplitudes in that sense. And they obey a number of identities such as cyclicity, reflections, and many other identities that are very neat and which have been explored recently. So these objects A, not curly A, the A on the right-hand side of that equation are actually much more convenient to work with if one has to calculate amplitudes. Now, string theory does many things, and one of the things it does is it gives a gauge gravity connection that was discovered long ago by Kawai, Llewellyn, and Tai, KLT relations, and they basically arise from the fact that you can view a closed string as a kind of product of two open strings. The open strings you can think of having gauge fields in them, and the closed strings has gravity. And in other words, if you have such an identity that a closed string can be written as a product of two open strings, you will have an identity between gravity and a product of two Yang-Mills theories. And that is precisely the origin of the squaring relation between gravity and Yang-Mills theory. So this is weird. It looks like it comes from string theory. Actually, it can also be proven directly from field theory, and this is something we did a few years ago. The names are on the bottom. And just to illustrate how that mysterious relation works, let's just consider just the simplest case, which is a 4-point function. So suppose we want a 4-point graviton amplitude, then that is written as follows. We call it M. It has, of course, 4 legs, 1, 2, 3, 4. These are bosons, and therefore they can be exchanged. So it's a symmetric amplitude, but it can be written as a product of 2 Yang-Mills amplitudes, as shown on the right-hand side. The factor in front is just actually, in this case, just standard Mandelstam S variable. We call it S12, but that's because it can be generalized to higher endpoint functions. Oh, maybe I should just mention briefly that it's an important fact that there are these correction factors of generalized Mandelstam variables, because clearly, otherwise you would have the wrong causality behavior, because an amplitude, just think of a single propagator involved. You would have then, if you take a square of such an amplitude, you'll have the propagator squared. And we don't want p to the 4 type propagators in gravity. And it is precisely the factors in front that take care of canceling unwanted poles. So, but there's a general formula for that for any endpoint, and I'm not going into it because it's not interesting in this aspect. It's just to illustrate that there is such a relation between gravity and a product of Yang-Mills amplitudes. So now we've learned that that gravity is a square of Yang-Mills amplitudes, and at the same time, in recent years, it has become extremely efficient to calculate Yang-Mills amplitudes at tree level to any number of legs and any helicities you want. And that means that also gravity amplitudes, despite the fact that in the usual perturbative gravity expansion are very complicated, because of this squaring relation, actually, they're quite simple to calculate. They're just the squares of Yang-Mills amplitudes at tree level. And because of what is known as unitarity cuts, actually that holds also at loop level, just with a slight little complication that you, of course, have to integrate over the loops, but the unitarity method relates the two amplitudes to each other. The second point I want to bring up here is something that's maybe a little surprising to some, which is that you actually can get classical gravity from quantum theory in the quantum mechanical loop expansion. And the loop expansion is normally believed to be an expansion in H bar. And if you look at the, for instance, the textbook of Itzik and Zuber, you can find a proof of that. But it's actually not quite correct. It is generically correct, but there are exceptions. And one of the exceptions is precisely gravity. So in gravity, the loop expansion is not a quantum mechanical expansion. It also contains classical pieces. And just intuitively to give an idea of why it is because gravity couples to the energy momentum tensor. So that leads actually to inverse powers of H bar. So you can have loops that have powers of H bar, but then if you have the energy momentum tensor canceling factors of H bar, you can get classical pieces out of quantum loops. And the simplest way to think of that and understand that is if you just take a simple Klein-Gordon equation, nothing to do with gravity, just to understand what's going on. If we put in H bar, which we normally don't do when we write down the Klein-Gordon equation, it goes at the inverse of the mass term. Or if you like, you can multiply by H bar square, of course, and then it goes with the derivative, because that's the difference between wave number and momentum. But the crux of the matter is that the H bar goes as inverse with the M term. And you now see that if you in a theory of gravity where amplitudes can be proportional to M, it will be in general, or energy, you can have H bars canceling between the loops and the prefactors. And that's precisely what's happening. Now we're going to look at the scattering of black holes from quantum field theory. Now we're not going to make a quantum mechanical model of black holes. We consider the scattering of point-like masses, but will be at very far distances so that we completely ignore the black hole features, like say the horizon. So this is large distance scattering or small momentum transfer, small t, Mandelstam t. And you can say that's a reduction of the problem, but actually almost all analytical general relativity approaches to scattering of two masses have to do that. And if you want to get into the regime where you're close to the horizon, you need to sort to numerical general relativity. So the situation is actually much simpler than you'd think, because it is really just the Einstein-Hilbert action coupled to scalar matter. And the massive scalar, it plays the role of the black hole. It's an elementary particle, you can say, but it's also a black hole. And we expand, as usual, gravity in the metric as shown. First, the Minkowski metric eta, and then a small perturbation, kappa, which is proportional to the square root of Newton's constant, and the fluctuating metric h. So if we calculate the first amplitude of that, the 2-to-2 scattering in gravity at tree level, indeed, and if we do the Fourier transform, indeed, we get Newton's law back. That's, of course, the way Einstein's theory is set up. It is supposed to give Newton's law in the classical limit and non-relativistic limit. And by the way, remember that anytime I'm talking about calculating in gravity here, I'm actually talking about calculating in Yang-Mills theory. It's not gravity. It's not needed. Gravity is not needed. We only need to do Yang-Mills theory and square it. So if you want to go beyond Newton, not just Newton's law, typically, if you look at textbooks, you will see the post-Newtonian expansion. But there's also another expansion, the post-Minkowskian expansion. So the post-Newtonian expansion precisely deals with the bound state problem in gravity. So say the orbit of Mercury around the sun or the Earth around the sun. And that's a double expansion in Newton's constant and v square, the velocity. And that is simply because they are of the same order in the bound state problem due to the virial theorem. So potential energy and kinetic energy. But there is another expansion that's far more interesting, especially if you want to look at the situation of gravitational waves. And that's the post-Minkowskian expansion. And that's an expansion in G only. So this is an expansion just in the coupling constant. And you're in a sense resumming or never expanding in the velocity. So you can think of the post-Minkowskian expansion as a kind of special relativistic general relativity, whereas the post-Newtonian expansion is a kind of non-relativistic general relativity. And the idea of using scattering amplitudes is to calculate the scattering Hamiltonian. Because if you have the Hamiltonian, at least in Newtonian physics, this is manifestly true. If you have the Hamiltonian, you can use it in all regimes. You can use it in the scattering regime, the hyperbolic regime, or you can use it in the bound state regime, the elliptic regime. And it's the same Hamiltonian. It's just the total energy that has changed. And the interesting thing is that the scattering Hamiltonian is precisely what comes out of a scattering amplitude. So we're all tuned up to calculate that Hamiltonian in the scattering situation, but applying it to the bound state problem. So how do we find the Hamiltonian? Well, in the scattering case in quantum field theory, if we don't have the antiparticles, and in this case, we're not considering anti-black holes because we're doing the large distance scattering, we're not considering annihilation diagrams. Obviously, we could, but that would be a crazy thing to do. So we calculate only the particle-particle scattering, and therefore you have a very simple called Saltpeter equation, a relativistic Hamiltonian, which does not have antiparticles, only forward-moving particles. And to calculate the potential for such a Hamiltonian, we know from textbooks that we have to calculate the amplitude. Actually, most textbooks say that the potential is simply the amplitude. Well, that's wrong in detail. It's correct to leading order, but there is a series of subtractions that have to be done. They're called bond subtractions. If you want to calculate the potential, you cannot just calculate the amplitude. You have to subtract certain pieces. They're all automatically generated by what's called the Lippmann-Schwinger equation, which I've written there. So there's a relation between the amplitude, the scattering amplitude, the potential, and it's a closed equation. It's an integral equation that involves these two quantities, and one can solve it in perturbation theory. Or one can invert it and say, here's the potential. If I know the amplitude to any order in perturbation theory, I know also the potential. Now, that is actually a full potential. It also has quantum mechanical pieces. But after having done that, we can also take the classical limit. And then that's precisely the potential, the classical potential we're after. So, and obviously then from the classical potential, we can calculate dynamics such as scattering angles, etc. And it involves an infinite series of bond subtractions. Now, that's kind of surprising that we need to calculate this potential with an infinite series of bond subtractions, because in quantum mechanics, we will never do that. If you want to calculate, say, the scattering angle in quantum mechanics, you cannot do the exact classical trajectory, but you can calculate the scattering. And there you'd only use the scattering amplitude itself. You would not do the bond subtractions. So how is that reconciled? How can that happen that in one case it looks like we should subtract something, in the other case we just need the amplitude? Well, that can be explained actually. So the first term you get in the Lippmann-Schwinger equation is the first bond subtraction, where you replace the amplitude by the potential, and you get this kind of integral, which you have to subtract. Now we expand that because we're in the large distance regime. So T, Mandelstam T, is very small. So we can do a Lorentz expansion in T. And it it's easy to work it out. It looks like this, where there's some parameter depending on energy. It's not, the details are not so important. Just to follow that there'll be an expansion because we're in the small t limit. And if we then substitute it into the Lippmann-Schwinger equation and take the classical limit, we get a relation between the classical amplitude and the potential, which is an infinite series. That's the way it is. So there is a relation like this, and just its effect. Now comes a surprising story, and I hope I will have time to go through it very quickly. If you now look at the Lippmann-Schwinger equation, at the Saltpeter equation, so this is simply classical kinematics, you can say. The energy relation, which is listed here. Total energy is conserved, of course. It's equal to the kinetic energies of the two particles plus the potential energy. And we can parameterize the potential as shown. If we now want to solve that equation, that energy equation, suppose we want to solve that in favor of p squared. We want to find out what's the solution for p squared. So that requires us to invert that square root equation. It's a little bit of work, not so hard. There's an infinite function theorem that tells us what it is. And it gives this. It says p squared, the three momentum in the center of mass frame of the two scattering particles, is equal to p infinity squared, which is the incoming momenta from infinity, and then something that depends on g, Newton's constant, because now there's also the potential terms. And there's an infinite expansion like this. And we can calculate to leading order, it is precisely as we expected. It is just the amplitude. And if you go to the next order, it's a somewhat more complicated expression. But the miracle is that actually the second derivative also turns out to be just the classical amplitude now in one loop order. Although it's a very complicated expression, it's exactly the same complicated expression we get from the amplitude related to the potential. So the weird thing is the Lippmann-Schwinger equation, the classical limit of that solves exactly the same equation as the kinematic equation of the energy relation, and all terms that involve the potential V disappear. So there's a deep relation between the Lippmann-Schwinger equation, which is a quantum mechanical relation. If we take the classical limit of that, we get a solution which is identical to the one we get from the energy relation of classical kinematics. This is only true in 4 dimensions, by the way. That's an interesting thing to think about. And it then gives a very, very simple kinematical relations between momenta and the amplitude. So P square is the momentum at infinity square with some correction that depends on the amplitude. So all we need is to calculate the scattering amplitude, take the classical part. In other words, put h bar to 0. So this, by the way, may seem, and it looks like the chairman is not interrupting me, so I still have a minute.
Well, you have a few minutes, 3 minutes.
Okay, very good. All right. So this may look like a very roundabout way to do classical mechanics, that we're taking a quantum mechanical theory, quantum field theory even, we're quantizing it, we're doing amplitude calculations in quantum mechanics, then we're throwing all quantum mechanical terms away, keeping only the classical ones, and that's, I claim, easier than doing the full, general relativity calculation. But remarkably, this is the case. And the reason is simply that general relativity, solving the classical Einstein's equations, is horrendously difficult if you go to even just one order beyond what Einstein could do in the 1930s. It took 50 years for people to calculate the first correction to that. And no one would know how many years it would take to calculate the next. But here we have a machine. We just calculate the scattering amplitude, take the classical limit, and there we have it. So there are things I knew I wouldn't have time to talk about, and I just mentioned it, which is indeed this relation between kinematics in classical general relativity, between kinematics and the scattering amplitude, the quantum mechanical scattering amplitude, where we're keeping on the classical limit. That is, of course, for the scattering situation. But again, I remind that once we have the Hamiltonian, we can apply that also to the bound state regime. The Hamiltonian is universal. It gives the interactions among the particles. And if you just go to the other energy regime where you have a bound state, it will be the same relation. And this is indeed what I'm saying there. And so therefore, this same Hamiltonian governs also the dynamics of two black holes, in particular, two black holes rotating so fast and so close to each other that they're emitting significant amount of gravitational waves. The last bit I want to say is that this is clearly only the conservative Hamiltonian. I'm not talking about radiation here. This is normal. That's also actually the way things are done in gravity when you have to calculate the gravitational waves from two black holes merging. You first calculate the conservative sector, and then afterwards you add on the radiation. There's a standard procedure how to do that. But the first step involves calculating the conservative sector, and this is what the amplitude gives you. All right, I will stop there.
All right, very good. Thank you. We have 2 or 3 minutes for questions. There are no hands raised so far. Are there any questions? Yes, Mauro, please. Go ahead. Mauro? You want to ask Nicolas Mavro Matos, sorry.
Yes. Unless Mauro wants, Mauro probably doesn't want to ask a question. Okay, I can ask it. Okay. Very nice approach. I would like to ask, what about anomalies? Yes, how do you represent gravitational anomalies in this approach?
So some people are speaking on top of me. So this is classical mechanics. This is classical general relativity. There are no anomalies. H bar is 0.
Right. So, but that's my question. If you want to, this approach of squaring things in principle could also work for quantum mechanics. For quantum
yes. That's another story. So the squaring relation, they hold quantum mechanically too. So right. so there's no issue there. I'm truncating that. But you can also calculate the gravity loops, of course, using that squaring relation and unitarity cuts. That's correct. Yes.
And you can get anomalies, I suppose.
You'll get, it's an identity. So you'll get exactly what you get from gravity. It's a one-to-one. I mean, there's nothing hidden. It's the same.
So nothing new, no more.
No, it's the same. It's one-to-one. It's an identity. Yes.
Thank you. Very nice.